Okay, so the camera is there.
Okay. Test, test. There's something coming through. It's not on. We need to turn
that
that
on. Yeah.
Yeah.
Oh, just it all. Oh, sorry.
Good.
I had to do that to turn on the audio video.
Oh, right.
Sorry about that.
Yeah, that's fine.
And that's it, right?
Well, no, we've got to share it.
Oh.
Welcome, everyone. If we can take our seats, we're going to begin the beginner session. And I'd like to open up with what's this thing?
Land acknowledgement.
Land acknowledgement. Thanks, Scott. The lands from which our members and guests are joining us are located on the original lands of the Anishinaabe, Cree, Ojibwe, Dakota, and Dene peoples, and on the homeland of the Métis Nation. We respect the treaties and get feedback. Out of it.
No,
Don't mess with that. Okay. We respect the treaties that were made in these territories. We acknowledge the harms and mistakes of the past, and we just dedicate ourselves to move forward in partnership with Indigenous communities in a spirit of reconciliation and collaboration. Thank you. And Scott, it's all yours.
Great.
Yeah, thanks.
Let's turn the lights down.
Yeah, that would be great.
Yes.
Well, hello, everyone. Oh, did you turn this off? No? Okay. Hello.
Yeah, that was good.
You're much louder than I am, Mark.
Oh.
Okay. Well, hi, everyone. I'm Scott Young, and I'm going to be doing today's beginner session, which is, it's warm. What should we look at? So many of us have, taken a winter time off, and we're getting all of our gear out, and, we're still in that wonderful period where it's not freezing and there's no mosquitoes. We've got about another couple of weeks of that. And so I thought I'd take a look at things that are up in the sky. How do you decide what you're going to look at? And what does looking at even mean anymore anyway? So we're going to take a look at a couple of different things. Now, you can look through a telescope and you can draw what you see. If you took a look at your recent Winicentrics, Jerry Shmochansky had some amazing sketches done with pencil and paper, just looking through the telescope with his eye and recording it that way. That were pretty phenomenal. You can also, of course, take pictures or do what we call astrophotography, where instead of looking through an eyepiece, you spend most of your time looking through a Windows troubleshooter on a screen. But eventually, when it works, you get pictures. I'm getting lazier and lazier in my old age. You can also have a telescope that you don't do either of that. You just basically hit the button at the beginning of the night and it runs through a pre-programmed segment of observations and you go to sleep. Technology has really allowed us to do astronomy in a bunch of different ways. So we're going to talk a little bit about looking at stuff and finding stuff, whether you're using a visual scope like your own telescope or one of the many loaner scopes that we'll hear about, or whether you're using a computerized imaging scope or a smart telescope or anything like that. The smart telescopes are becoming very, very popular. We've seen lots of images from them, and lots of members have them. They were out at Astronomy Day in en masse, and people were pretty impressed with the kinds of views that you could get. But people were also pretty impressed looking through the eyepiece, especially new folks, where they don't really know. They know they like space, but they don't really know quite what that means. When you see something, whether it's on a screen as a live view or whether it's looking through an eyepiece as a live view, it's pretty powerful stuff. And we saw, I don't know, does anybody know how many people were out at the park on? Anyone want to guess?
In the evening?
Yeah.
At least 500.
Yeah?
Yeah.
Okay. I think it was more than that, but I don't know how long they stuck around. Some of them might have stayed like that whole night. So yeah. But yeah, it was a great group. Sometimes, we had this kind of situation. This was not from last night, but we saw this kind of stuff as well, where you have someone getting their very, very first view through a telescope, and it's pretty hard to beat that. So let's talk about what we can see and how we can find it. In my second year of my physics degree, The professor came in on the first day and he said, okay, everything that you learned in high school is basically wrong or at best an approximation. And then he threw a couple of things up there. And this was one of the images. This is the universe. 74% dark energy. What's that? Nobody knows. 22% dark matter. What's that? Nobody knows. We got some ideas, but it's invisible, so we really can't prove it. 4% is atoms. You, me, stars, galaxies, things we look at through our telescope. So 4% of the universe is all we can see through our telescope. The rest of it, can't see it. Well, this is 4% of the screen covered with little blue squares. So imagine just randomly pointing your telescope and hoping to see something cool. That's not the way it works. People often get a new telescope and they are frustrated by it because they think they can just point it up in the sky and the wonders of the universe will be revealed to them. Not so much. Now, this is actually an overstatement of how much cool stuff there is. This is 4%, but that assumes that all of the stuff in the universe is visible in our backyard telescopes. I mean, some of it is not glowing. Some of it is dust or planets or invisible. So we'll take some of that away. And then some of it is far away. So it's really, really faint. So we'll make some of it fainter. This is the universe you can point your telescope at. And if you know anything about telescopes, your telescope only sees about that much of the sky at any given time. So as you can see, just randomly pointing your telescope at the sky, odds are you're going to see the most common thing in the universe, which is boring empty space. This is why people often get frustrated with their telescopes. This is also why the push to having telescopes that can find things for you has been a technological dream for many years that is now sort of realized with the smart scopes. But you have to point your telescope precisely to be able to see something interesting, whether it's to look at with your eye or to take pictures of it or anything like that. When I'm observing visually, this is the book that I take with me. It's Night Watch, written by Terry Dickinson. I think it's in its, I don't know, 7th edition now. Ken Hewitt-White took it over after Terry passed away a few years ago. And it is it's your desert island astronomy book. It has everything in it. The part that I'm talking about right now is the Star Atlas, all the Northern Hemisphere constellations in chart form with all the cool stuff plotted out, the highlights, if you want to see sort of the biggest and the brightest and the best. So I highly recommend that. There's a follow-on, the Backyard Astronomer's Guide, which is really more about gear and techniques and things like that. Doesn't have the same level of usability at the telescope, but also a very good book. Of course, you can use software. We have been promoting the program Stellarium here for a number of years, and it is a free software program you download, tell it where you live, tell it what time it is, and it shows you the whole sky. And you can either make charts like this, or you can print out charts to take out to the telescope, or you can plug your telescope into your laptop and just click on the mouse and the telescope can move to that appropriate spot. A very, very powerful tool for planning what you're going to look at, finding things, tracking them down in the sky. That's the same picture. I'm training a couple new staff at the planetarium. Rhiannon will appreciate this. So it turns out that constellations, the official 88 constellations that cover the whole sky, they only became official less than 100 years ago. And most of them are garbage. I don't know if you've ever tried to find constellations, but they don't look like what they're named after. So we're trying to ditch some of the classical constellations and just go with asterisms or easy to find star pictures. This is the Summer Triangle. Amateur astronomers have known about this for a long time. 3 bright stars. And right through the middle of it, we have, where's our laser? The Milky Way. So even if you're in the city and you maybe can't see the Milky Way because your neighbor won't turn their lights off or something like that, or there's just too much light in general, if you can find the Summer Triangle, 3 of the brightest stars in the sky, you know the Milky Way goes right through that. So that can help you track things down. Because the way space works, our Milky Way galaxy has a particular shape. And if you want to see cool stuff, there's a lot of it in this region of the Milky Way. Now, the Milky Way goes all the way down to the southern horizon. We get a terrible view of it from here in Manitoba, but if you ever go south, you get a very nice view of the Milky Way. My images of the southern Milky Way always look sort of yellowy brown because we're looking through so much atmosphere that it really doesn't show like it does in somewhere, say Chile or Australia or something like that. Right about there is the center of the galaxy. So if you want to look towards the most stuff, that's the direction you want to look. And it's terribly placed. That's the best view we get from here in Manitoba. It's about, 10 degrees above the horizon. So we have to content ourselves with the less rich parts of the sky, but that's still got a lot of really impressive stuff to see. Just as a reminder, here's the Milky Way galaxy as seen from the top. We've got the big core with a supermassive black hole in the middle there, and then surrounding it, a lot of stars, fairly densely packed. And then out on the spiral arms, there are all sorts of relatively new stars, as well as the dark dust and the little red glowing nebula and star forming regions and so on. You are here. That's not the size of the sun. That's just an indicator. The sun is microscopic here, but that's about where we are in the Orion arm. When we look towards Sagittarius, we're looking in towards the core. When we look towards Cygnus, which is one of the stars in the summer triangle, basically is one of the stars in Cygnus, we're looking along the disk of the Milky Way. So even though we're not looking right into the center, there's still lots of stuff here, nebula and dust clouds and star clusters and so on. And even when we look out this way towards Cassiopeia, there's still stuff there because we're looking along what is a flat plane. The Milky Way is basically a big round pizza made out of stars. And it's not deep dish pizza either, it's thin crust. So maybe 1,000 light years across. So if you're here and you're looking in towards Sagittarius, towards the center, anything that you see could be anywhere from where you are all the way through here and even towards the center. You're probably not seeing stuff from over here though, because the galaxy's in your way. It just blocks your view. But if you're looking this way, up out of the plane of the galaxy, anything you can see can only be at most that far away from you, 500 light years or so. That's the direction we're looking right now. If you go outside tonight and you look up, that is the area that we're looking at. We're looking through the thinnest part of our galaxy and then out into intergalactic space. So we don't see a lot of galactic things like star clusters or nebulas or things like that. There's only a few of them in this little region. But out in this direction, there are lots of other galaxies. That's why spring is sort of galaxy season. I jumped ahead just a little bit here. So the season of the year basically determines what part of the galaxy we're either looking through or out of, and that determines the kinds of things we can see. So if you want to point your telescope at some of these things, this is the most common problem with telescopes. If you've got a new telescope and you can't make it work, 95% it's because your finder isn't lined up. It's a very simple operation. Once you do it, very, very easy to do. It takes just a little bit of adjustment, but almost everybody that calls us at the planetarium and says, hey, I can't get my telescope to work, it's almost always aligning the finder. So that's something we can show you to do at the members observing night, tomorrow night or any other night. And so if you've got a telescope and you're having trouble with it, you can also use this internet thing and Google it, and you will find all sorts of information on how to align your finder. Critical thing to do. You got to do it every night. At least I do, because my telescope gets bumped around or whatever. So very, very important. I'm going to skip over this image for now. Now, if you've got a go-to scope or a smart scope, a computerized scope, you don't have to worry about finders, telescopes, or any of that. You just sort of plunk it down and press the button and hope that the black box works. And it almost always does. If it doesn't, I can't help you. It's one of those things where you put a lot of trust in the technology, and it is 100% worth it when it works, but very frustrating when it doesn't. A go-to scope, it's much easier to find things, but here's the problem. The little handset that these go-to scopes have including the one in our observatory, contain, I don't know, 15,000 objects or something like that, or maybe more than that. And all they do is give them a name and tell you where they are. You have no idea what it looks like, how big it's supposed to be, how bright it is, anything like that. So if you just sort of randomly surf through the remote looking to see, oh, I'm going to look at NGC, blah, 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 you might get a great view, or you might get something that literally your telescope can't show. So while it's great to have these tools, you still need something like Stellarium to look at and say, hey, this is a galaxy and it looks like this. And so I know what to look for in my telescope. A little bit of planning for your observing really goes a long way because, and I've done this, I don't know how many times myself, you get out there, it's a beautiful night, you've got your telescope set up. What should I look at? And then you wind up looking at M13 again. Because that one's easy to find and it's bright and it's beautiful, but I mean, I could do so much more. Anyway, there are so many things to look at. Put in just a little bit of effort and you can get away from always looking at M13. For visual observing, this is the most important piece of equipment that you have. And again, since this is the beginner session, we're going to step back a little bit here and just remind people how your eye works. Here's your eyeball cross-section. The lens at the front, a pupil in the middle, and that pupil can open up or close, and that's what collects light. And the light hits the back of your eye, and magic happens in your brain, and we see an image. The more light you get into your eye, and the more light gets detected by your retina and the optic nerve, the better your view is. So let's just schematicize this a little bit. Your pupil, in photography terms or telescope terms, is called the aperture. The aperture is the open end of your optical system. And even though we think about telescopes as the optical system, the Mark I eyeball is equally a optical system. It's an adjustable one. So in the bright light, your pupil closes down a little bit. As you get older, tends to squeeze down a little bit more. And then when the light is faint, it will dilate or open up. And when you're young, it opens up really wide, maybe 8 millimeters. When you're older, 7, 6, 5 millimeters, not nearly as much aperture. That's why we tend to see less as we get older. One reason. Okay, so we've got light coming in from the universe. Well, we'll skip the math. And the only light that we get to see is the light that makes it through our pupil and into our eye. All the other light that has traveled for, millions of years and made it through the entire universe literally bounces off your face. And that's a waste, I know, but some of it gets into your pupil. So the first thing to get a good view is to make sure you have your pupil as wide as possible. That means you can't look at any light. Any light. Even a red light. I've seen people with red flashlights out at the observatory, and you could fly down airplanes with them. Like, they're so bright. They're red, which reduces the effect on your night vision, but just the amount of light can be very, very, can really mess up your night vision and make the pupil shrink down. So you want to have dim red light. Ideally, you want to have no light. You want to be able to operate your gear in total darkness, but we're always going to need some sort. So a very faint red flashlight is something that I recommend. Again, skip the math. If you keep your pupil fully dilated, more light gets in your head and you can see better. So that's the number one thing. It doesn't matter what your telescope is doing. If you're looking at your phone every 30 seconds and your pupil is shrunk down to a pinhole, you're not going to get a good view. And it has nothing to do with your telescope. It has everything to do with the eye. Now, a telescope is just a funnel for light. Its job is to get more light into your head. So you're taking a big funnel here, and instead of that light bouncing off your forehead or whatever, you're actually getting a whole bunch more of it and you're funneling it into your eye. More light makes a brighter image, makes a more detailed image, and we can see more. So that's kind of that's what telescopes do in a nutshell. And so the bigger your telescope, the more light gets in your head. So when you're observing visually, you want to be in a place where it's as dark as possible. You want to be in a place where there's not a nearby light shining into your telescope or shining in your eyes so that your pupils stay nice and wide. And then you want to be able to point your telescope accurately at whatever you want to see. We can't always control all of that. My neighbors have someone broke into their house like 10 years ago, and so they have about 4,000 candle power spotlights all over their house. And I tried to, anyway, it's a long story. Between that and trees, my backyard is not a great place for observing. So what can you see? Well, lots. The universe is packed full of stuff. If we just go through some of the highlights of the spring sky, like if you go out right now, if it was clear and you could get a good view of the sky once it gets dark, there's little places where there are multiple galaxies in one spot. This is the Leo trio, or M65, Messier 65, Messier 66, and New General Catalog 3628, that romantic name of the third galaxy at the bottom. This is a sketch that I made using the center's 14.5-inch Dobsonian that's out at Glenlee. And it's just paper and pencil sort of smudged around with my finger to try and make it look realistic. And then I scanned it and flipped it around so it looks like white stars on a black background. So it looks a little more realistic. No technology, no anything, basically. And I had the side benefit that the photons of light from those galaxies, which are 30 million light years away, I think, if I'm remembering correctly, entered my head and are part of me now. Like there's that physical connection between me and that. Now, I've also imaged this same galaxy using a 6-inch telescope and a CMOS camera with some color filters, and I got this. And this is pretty nice image. I'm happy with it. I'm sure I could make it better, and I could take longer exposures. You're never happy or completely happy with your images, and so the quest to make things better is always there with astrophotography. But this is a different kind of satisfaction for me. The immediacy of connecting with the sky directly versus the ability of recording a detailed image and making it as good as you can. Both totally valid ways to look at the sky. They're just very different, and they require sometimes different paths, different skill sets. But as we're seeing now, we've got lots of active observers using visual, lots of active observers using various detectors and cameras and things like that. So galaxy is a big hit right now, and there's lots of them. They come in different shapes. These are some more galaxies in Leo. I like it when there's more than one, because that way you get sort of a compare and contrast kind of thing. There are some star clusters, which I used to always give short shrift. I would think, oh, star clusters are boring. It's just a cluster of stars. But you can see them on a night when it's full moon. You can see them on a night when the conditions aren't great because the stars cut through a little bit better than that fuzzy stuff in nebulas. Then there's globular clusters. This is not M13. This is M3. And you might think, well, you've seen one globular, you've seen them all. Totally not. They're all completely different. I didn't used to think so, but one of our members back a long time ago pointed out to me the differences, and they're actually quite interesting when you look at them individually. Some of them are very broad with the stars spread out. Some of them are really compact in the core. Even when you see similar objects, they're all very, very different. So you'll never really run out of things to look at. This is some galaxies up in the Big Dipper, M81 and 82. And as you can see, different styles here. There's the big spiral galaxy on the bottom. And this galaxy up here, this is M82. It's also kind of spiral, but we're seeing it edge on. But it's got some weird things going on in the core there. And then there's this little blob over here that actually looks better not projected on the screen, but there's little dark clouds over the nucleus and things like that. Really, really interesting things to look at. Now, when you look at these visually, you might not see quite that level of detail, but again, you're getting that immediate connection. And there's no real way to reproduce the view through a telescope. Like, this is not what it looks like. The colors of the light that we see with our eyes can't really be reproduced on a screen. And so it is a very different experience. And I highly recommend that even if you've done, visual in the past, make sure that you get out and look through telescopes as well. I'm going to skip along a couple of these here. Oh, does anybody know how to get rid of internal reflections? This is affecting all of my images now. And so instead of spending all my nights imaging, I'm going to spend all my nights trying to figure out where that band of light comes from. So whereas when I'm looking through my telescope, it's not there and I can ignore it. So again, different paths, different problems, different obstacles to overcome, but still an enjoyment of the cosmos. I wanted to skip ahead here to, okay, so we talked about this last month, I think. If you go out and you look towards the Big Dipper, and then if you imagine the Big Dipper had a hole in it, water would sort of drip down the southern sky and land on the back of Leo. And then off to the left of that is Virgo. Virgo has this big cluster of galaxies. This is called Markarian's chain, after the person who first sort of brought attention to it, Wilfred Chain. Yeah. These are, M86 and M84 are big elliptical galaxies. Here you've got a couple that are like ripping each other apart, having collided in the past or passed through each other. And when you look at this image in detail, there's a whole bunch of little ones. Like there's even ones here. This one doesn't even have a name. I mean, it probably does in some bigger catalog, but there are objects on here that reach 19th magnitude, which when I was a kid, I remember I think what's the big telescope on Palomar? I forget the aperture, but magnitude 19 was its sort of limiting magnitude. And I thought, wow, that's amazing. No. And now I'm doing it from my backyard with a 6-inch telescope. Oh, where did it? There, M13, there you go. Definitely a highlight. And the thing about globular clusters is that when you image them, they look like this beautiful cluster of stars. And when you look at them, they look exactly the same. They're the one object that actually looks visually like the images. So really great things to look at. They're usually, the brighter ones are high surface brightness, so they cut through light pollution and you can see them in the city and things like that. They really are a great target. And often they're quite easy to find and I remember where they are. And so if you come to a public event and you come to my telescope, 50-50 chance you're going to see M13. I wanted to get, sorry, there's a bunch more pictures here, but we don't have time for them. I just wanted to get to my sketch of Markarian's chain, but it did not. Oh, did I skip over it? Maybe I skipped over it. With the same telescope, the Dobsonian telescope, I sketched Markarian's chain. And normally when you sketch, you draw a circle like this to represent your eyepiece, and then you draw. I just started drawing and then I just kept going outside the circle until I ran out of paper, and I covered a full sheet of my sketch for Markarian's chain. And in that 14.5-inch Dobsonian, it pretty much looks like this image. Sorry, this is all going backwards. It pretty much looked like that visually, which is a sight to see. So whatever telescopes you have, remember the center has access to big Dobsonians, small telescopes. We've got a smart telescope. We've got an observatory. Other members at the observing sessions, the members observing nights have all sorts of things as well. Come on out, make use of the equipment that's available to you, the community that's available to you, and explore the cosmos as many ways as you can. And that will give you a experience that you can't really beat. So thank you very much.
Thanks, Scott. It was excellent.
Yeah. It's great.
I'd like to take a quick opportunity to make a presentation today with Dennis Lyons, our former president. If you wouldn't mind coming forward, Dennis.
Is everybody on the water balloons ready?
Oh, we missed you at the last meeting, Dennis, but anyway, Dennis has been president, I think, over 2 or 3 terms. Served us very well, took us from kind of a grassroots organization through to a legal non-for-profit, and organized us very methodically and completely. So I think the council and membership wanted to acknowledge all the work that Dennis put in, as well as his work with National, which he's now on the board for, especially given their financial crisis. And we want to just say thank you, Dennis. So thank you very much for all your work. And with that, I guess we'll move on to announcements. Let's see, page down. There we go. Nope, that didn't work.
There's the clicker.
It's the clicker. The mouse or the clicker? Okay. Okay.
Button towards you.
I heard something else moving. Okay. On the computer or on the? There. Yeah, I'm using the down button. Okay.
Let's see here. Sorry. Why is this not working? Come on.
That's the Zoom when they have to go back to the
These are right. Maybe try it again. See.
Try it again.
Yeah.
There we go. Okay, we did the beginner session. We did, okay. Does it just delay? It's not moving again. Which button did you hit to go down here? There we go. Okay, announcements. Finally. Some brief announcements, and these are a little repetitive. I've tried to start cutting them back a bit. I just want to acknowledge a few folks in the crowd today, or perhaps not, but we have a fundraising committee, which I think we've talked about every meeting pretty well, and Wing Kwong is in charge of that. He's in the back row there. Hand up, Wing, thank you. We have one major event or one major program underway, and that's Telescopes for Kids, which he's looking for donations to purchase equipment for those young upstart astronomers that we want to encourage to become RASC members. So any help we can offer Wing would be appreciated. Stan Runge is running our Explore the Universe program. He's in the audience today with the Science Rendezvous red sweater on. You can't a red shirt, you can't miss him. Mike, also in the audience, runs our Lunar Scope program, and we'll hear a little bit more about that as part of the discussion tonight at our center. I talked about Telescopes for Kids already in conjunction with the fundraising. And I also mentioned Science Rendezvous. That's an outreach program that we've worked with the University of Manitoba over quite a few years. And it's a tremendous effort that the university coordinates and invites us along. And we have a booth and we have volunteers that participate in that program. Last time it was done, which was 2023, 2024, unfortunately had some disruption with some protesters. So they deferred it. And this year is our first year in 2 years. But they had 20,000 people go through that program over the weekend. So, and our booth was a major attraction. We had lots of people stop by to look at the sun and the moon, whatever was up, and ask lots of questions. And they were from, 5 to 80. And with that number of people, I'm sure people that are volunteering would more than likely and even in my case, I've came across people that I work with, I'm friends with in other parts of my life, and they come through the university and connect with you, and you have a chance to discuss your hobby with them. So that's really a terrific opportunity for volunteers from the organization, and Stan's been great at coordinating it for a number of years. So I really appreciate that, Stan. Astronomy Day was very successful. I heard estimates upwards of 500 people attending the evening event. We weren't quite that high during the day event, but nevertheless, we were there from 1 till 4 in the afternoon, and then from about, I guess, 7, 9 when it got dark until 11:30 when the park closed. And that's when the majority of people came by, and our telescopes were humming. and we're a busy group. Coming up, we have another outreach event. It's at a daycare, and we can always use membership help there. These are kids from anywhere from 4 or 5 years old up to about 10 or 11, and 90% of them are just love the opportunity to look through a telescope. It's during the day, and it's only half a day though. It's from 10 in the morning till just after lunch, and the kids eat it up. And we usually have a couple presentations going in the gym, and then solar viewing and lunar viewing at out in the yard. It's at Carpathia School on Grant, if you know where that is. It's in River Heights, and they're just a terrific group to work with, and it's hard to say no to them when they ask. And we also are looking for volunteers, of course, for Sprucewood Star Party. We have a Glen Lee 50th anniversary coming up, so if anybody has any budding ideas about what to do for that, believe it or not, that observatory has been there 50 years as of next year, 2026. So we'd like to think about what opportunities there might be to help club celebrate that. Now, of course, we talked about workshop outreach, and then the members only nights tomorrow night at the observatory. We just wanted to add as well that this, as of I think this week, we decided new members and existing members will be added to the groups.io main page automatically. That wasn't happening. You had to opt in kind of by making an overt effort to do it. That wasn't probably the best approach for new members, because it took some kind of action on their part, and they would likely miss out on any of the discussions or messaging or events that might come up on the main page. So what we've decided that if you are a new member, an existing member, and you're not on the main page of the groups.io, we're going to put you in there. And if you decide that you don't like to get the information coming through onto your email, you can always let us know and we'll take you off. But from this point forward, you at least get onto the main page. And then from there, you can elect into the subgroups. And there's a number of subgroups available for specialties. If you're a solar observer, you're a visual observer, you're a sketcher, you're a deep sky observer, there's a buy and sell. There's just a myriad of opportunity there for members. So take advantage of the groups.io site, and we will have you in there, at least on the main page, to get the initial communications and the general communications. If you have a general question, somebody asks you a question you don't know the answer to, put it up on the main page. You'll get a response from an astronomer. Other than that, I guess we wanted to also bring up that we're planning to do some construction work at the observatory. And if you have access to bobcats, skid steer, flatbeds, trucks, construction materials, if you could actually let us know, because we'd really like to be able to renovate that observatory, create a bathroom that isn't part of the actual observatory, and locate it in an opportune spot, which would also theoretically be shared with the university students who are out there. They don't have a bathroom either. But right now, to use the bathroom, you have to get access to the actual main telescope dome. And what we'd like to do is separate the two. And then also that gives us an opportunity to finish reparations for the last flight. So anyway, if you have access to this really important construction type equipment and more importantly, expertise in this, we'd really like to hear from you at the Observatory Committee. So I've probably spoken more than my allotted time on announcements, but this is all very important stuff. And if you do have any suggestions or help that you might be able to offer, you can speak to me at the break time, or reach out to the main page, the groups.io, or even my own email address. The president, it might still go to Dennis, but he'll get bombarded until he tries too much. But president@winnipeg.rasc.ca. So if you can offer any of that, that would really, really be appreciated. And love to hear from you. Anyway, that's all I have for now. And I think the next thing we're up to is, let's find out. Let's see if the pen works. Oh, no, wrong way. Oh, no, that is the right way, right? Okay, we've gone that way. And so now I guess I need to introduce our own Jay Anderson for what's up this month. But we have a TV audience, Jay. Everybody knows who you are and who's here, but we have a TV audience now, so you could be broadcast all over the world.
I've been here long enough that I built it, Glenley.
Switch it over here.
So did Judy for that matter, and Stan and.
Escapes. Is this it? This is it here, right?
What are we using to change slides these days?
This should work. Go down. No, okay. I don't know why it stopped working, but anyway, these two keys just goes down.
All right,
Okay.
okay. Every computer's got a different key. I program my computers to be stupid, so if you push the space bar, you change the slide. Some do, some don't. Well, we have a kind of a quiet month right now for two reasons. One is we're in between where things are really happening and where things used to be happening. So there's no comets that are coming in to illuminate us, but we have a few things that to look out for this year and this time of year. Again, we're fighting daylight, and I showed you this last month. Now that box outlines where we are, well, that's our next month, and you can see there's only a little nose there in the bottom inside that box where we actually get all of the night sky, all of night darkness, and that's only for about an hour and a half. Peaks at about 1:30 or there a little after 1:30 at night. So if you want your darkest skies, you got to get there at 1:30 and or maybe at midnight and stay until 2. Nothing convenient about this at all. On the other hand, it is actually pretty decent observing within astronomical twilight. So from probably about 10:30 on to 2:30, you can actually do observing, especially if you want to take some of those brighter objects like Scott mentioned in the sky. So what have we got here? I talked last month about the realm of galaxies, which is in the in around is it which end of this works? Anyway, there we go. The realm of galaxies is in here between Leo and Virgo, and particularly in this little basin of Virgo here, but also in here and a little farther toward the west. So what we really have here is the Milky Way is this band down through here up on the upper left edge. And the Milky Way band is just rising, coming over the horizon here at midnight, which is still early in the night. You want to maybe be there at 1, in which case it'll be a little farther advanced. Tonight or tomorrow night we have a lot of moon, but that's going away. And then we see the realm of the galaxies is fine viewing in here. And your brightest star is Arcturus, so it gives you a sort of viewpoint on where things are in the sky. And Regulus in here is pretty bright as well, so you can go between the two of them to and to Spica here, or the moon if you want to give yourself a lot of trouble and go observing. But in that box is where those nebulas are, or the galaxies are that they talked about. The North American nebula, I always look for this sort of thing. You're getting up into, oh, that's how you change your slide. You're getting up into Cygnus in here that God talked about. This is Deneb, and Cygnus has got a couple of little goodies. One is a North American nebula here. You won't see that by eye, but it's really easy to photograph. And of course, we have our old favorite, M13, which is also fairly high in the sky. It's kind of like a preliminary of the Milky Way. And of course, here's the summer triangle. So when you see the summer triangle rising, you know that there's not going to be any more darkness for a month and a half. And but when it's gone, it's going to be nice and high, and that gives you the sort of core of the Milky Way, or at least the northern part of it that we see. So you just take a different perspective on tonight or 2 nights from now, you can see the Milky Way rising. Here is Sagittarius's core. We're now looking at midnight again, a little earlier, so it will be slightly higher if you wait that extra hour until you get the maximum darkness. Cygnus is up in here. There's a few little goodies down alongside Cygnus in through here. But this stuff is going to be low down for you, and it's not going to show to its best point of view. You might be restricted in the things that are higher. M13, the globular cluster, and Hercules is up here. This is the keystone of Hercules. We'll look at that in the next slide. And it's easy to spot between these 2 stars here. It's a good binocular object. And over here, also easy to spot, but difficult to see, is the Ring Nebula, which is kind of tiny for a telescope or for binoculars. You need a telescope, but those 2 are nicely framed between 2 stars and relatively easy to find. So here's a close-up of Hercules and the keystone of Hercules here. And then the M13 is about 2/3 of the way from the bottom star to the top. If you want, you can go looking for M92 up there, which is another globular cluster. It's actually one of the things when I'm out with binoculars, I always try for, just because it's so easy. It's an obviously fuzzy star in that area. Of course, if you take a telescope to it, you get this sort of an impression of it. What's interesting about M13, if you feel like a challenge and you've got a telescope, there's a nice little galaxy up there above it that you can go in search of as well. We get into June, you can see that by the time, now we have no darkness at all, but I'm trying to pick the darkest part of the sky, and even the software program is kind of giving me a bluish type of sky, but the Milky Way is now a lot higher. Sagittarius in here is getting close to the southern point, which is when it'll be at its highest. And it's kind of unfortunate that Sagittarius is at its best when we have such a bright night sky, but of course all we have to do is wait a few more months and Sagittarius will be at its best in August, but earlier in the night. The ecliptic, which is the proximate path taken by the planets and exactly the path taken by the sun, is low down close to the horizon at this time of year. So the full moons will be traveling down into this part of the sky, and they're not quite as obtrusive if you want to look at something that's farther to the north. The planets, however, are also down low, but there are no planets that are anywhere out in the night sky. They're all in the morning or evening. So here we are looking in mid-June, 1 a.m., getting close to the darkest time. And it's worth taking a look at Sagittarius even in June, because you're looking away from the north, and the north is where the bright skies are. So you're looking into the darkest part of the sky when you get into mid-June. It's full of all kinds of stuff. There's a list of them down the side here. I probably could have found a better planetarium program than this, but I've marked some of them out here. The yellow ones are globular clusters. The red arrows are nebula, and the orange arrows are open clusters. And 2 of them are here. This is the Trifid and the Lagoon Nebula, which are M8 and M20 in here. I've got pictures of M16 and 17, but look at all of these. Globular clusters tend to cluster around the core of the Milky Way, so that's why you see so many of them in through here when you start examining this part of the sky. Sagittarius itself is this teapot. Here's a handle and a spout and so on. Once you recognize this sort of asterism, it's you can start finding your way up in here, but actually cruising through here with binoculars will show you almost all of those items. It's not the sort of place where you really need a big telescope, except to see it a little bit better. And the Scutum here is the constellation, but that's where some of the best star clouds are in the Milky Way. Here we have the Eagle Nebula here and M17 here. So these are difficult to see in this extent. These are hour-long exposures, but at the same time, you will see the associated clusters with them, and you will begin to see the fuzziness, but probably you'll have to wait until later on in the year when they're into darker skies. The planets, here's a comparison of where they are. It's kind of a thin month for planets because you can see Jupiter's low, Mars is high, but it's getting really faint. Saturn is getting up in the morning, but so is the sun. And Venus is really bright because it's close to its maximum brightness, and it's at its greatest western elongation. That means it's at its farther western point from the sun. So tomorrow, during the activities at the university, taking a look at Venus in the daytime, or even by eye, once you find it, you'll be able to see Venus by eye in the daytime, and then check it out with binoculars and the telescopes we'll have. So that would be actually a nice target tomorrow. Once we get in later on in the month, Jupiter's even lower down in the sky in the evening. Mercury, which is now invisible behind the sun, will start to come out in the west. But also because the ecliptic is very low, so will Mercury be very low. So instead of coming up nice and high, it'll be coming out at an angle close to the horizon. Not as nice to look for because Mercury needs to be high in the sky to really see it decently. Mars is getting fainter. You can see that it's fallen by another 0.2 magnitude, but it's close to Regulus, which is not too difficult to find. Saturn's getting up a little higher though, and getting a little bit brighter. Like Venus is still bright, and it's following in behind Saturn. You can see the reason for that. Here we are on the Earth here, and when we look toward the sun, we see Venus a little off to the side and Mercury behind it, and Mars is here. Take note of this because if you know the way the Earth rotates and everything else, you think, oh, he's got everything backwards here, but you're not looking at it from the top down, you're looking at it from the bottom up, so all the rotations go the other way. I did that to confuse everybody. And here we are with the outer planets. Of course, we don't have a problem with the sun being on the other side of them. We have a problem having to look through the sun to see them, which is what we have to do with Jupiter. We're very close to it. Jupiter is very low in the sky. Saturn, however, is up on the morning side and coming up a little better. We also have Vesta, which is one of the bright asteroids, and it's somewhat to the east side of Spica here. A little bit hard to find because it's at magnitude 5 and a bunch. But from May 14 to 30th, it sort of cruises through that angle. You'll need a pretty high resolution star chart to be able to find it. Perhaps the best thing at this time of year is noctilucent clouds, which are something we see in the summer. They're the highest clouds in the atmosphere. They have a distinct bluish color, as you can see in the video here, and even in this. This is the magnification of this scene. We only see them from our latitude up to about 70 degrees. Beyond 70 degrees, the sun's up all the time, and below 45 degrees, they're too low on the horizon because you only see them when the sun is below the horizon and illuminating the clouds. You can see here in the video how they sort of shrink down toward the horizon as the sun settles in this video. And they're not difficult to see. This was taken from Assiniboine Park. So they're pretty obvious when you see them. You just wait till the sun's about 6 degrees or so below the horizon and start looking for these bluish, lacy clouds that are up there toward the north, northeast, and northwest in the sky. And that does it. We've got sun coming up, and that's all I could find to look for this month. Okay.
Thanks, Jay.
Stop sharing.
Okay.
Matt is coming.
Oh, okay. All right. Hey. Sure. Here. Share. Okay. Now okay. Don't know if we have Matt Kopko here. Actually, it's Stevens. Yes, we had that connection. Oh, he is. Thanks, Matt.
Hello.
Welcome.
Yeah, I've never worn one of these mics before, so.
Okay, well,
There's
there's the battery pack that goes with it, and I think this is the. Let's see if the eye is on this side.
Okay, I don't really have any visuals.
You don't have a visual?
It's more of a tell than a show. really.
There's that. Okay. Yeah, well, there it is. There, the red button there is the. Okay, and there's the
Okay.
battery pack. Okay, thanks, Matt.
Hi, my name is Matt Stevenson. I've been coming to these since last fall. I think this is my 7th one, but I've been an astronaut for about over 50 years now. Okay, I'll just stick that in there. I will be reading from this. Is there a light I can get? If not, I can read like this. Okay, yeah, great. Okay, I have an interesting story to tell. I'm not a part of it, but I was present at the very beginning with the main guy. And of all the classmates I've had in science, he has actually achieved what they call scientific immortality. That is, he's had something named after him. The name of my presentation, I call it Son of Kopko. I'll explain that in a moment. Okay, it's a Ukrainian name. It means, my friend Matthew Choptuik, that's his last name. I've already posted a link on the group there to an article about this and a couple of pictures of Matthew. Okay, so yeah, it's a Ukrainian name. It means son of Kopko. Kopko is a popular first name for boys in the Ukraine, and or was at an earlier time. Matt's dad was not named Kopko, but some ancestor surely was. Before I tell the main story, I will spend 1 minute telling you the part that you may not believe happened. I myself am still surprised, but it happened all right. In the summer of 2002, I was reading Time magazine. They had a section called something like 40 under 40. It was about people no older than 40 of them who were all excelling in their fields. I'm reading this article, and about 2/3 of the way through, I said to myself, pretty soon I'm going to see someone I know in here, and it will probably be Matthew Choptuik. And I turned the page, and there was Matt. A piece about this bet that he did. He helped a couple of guys with a bet they had made with Stephen Hawking. So this is what that's about. Actually, I will start at the beginning. When I studied science at Brandon University in the late 70s, I had a classmate who was younger than I was. I was used to being the youngest student in my class ever since grade 3. I had just turned 17, which I thought was pretty good. Then I got to know Matt. After a few months, November came along, which included his 16th birthday. Not bad for a university freshman. One day while we were walking around, Matt told me what he wanted to do with his life. He said he was going to learn everything he could about physics and everything he could learn about computers and become an expert in simulating anything you could think of. I knew he was brilliant enough to do it and to excel at it over the decades. More importantly, he was brilliant enough to conceive of it because he had already mapped out his career in his early teens. He was 15 when he told me this, and he actually did it. Considering that our understanding of physics improves all the time, and also computing power doubles every year and a half, there should be no potential ceiling on this field. It should just be able to improve forever, you know? Matt did not name his specialty numerical relativity, but it's a good description of what he does, because for the most part, what he does is astrophysical simulations. He's not actually an astrophysicist, but it's a large part of what he does. And because of the velocities and timescales involved, relativity is built right into the proceedings. So numerical relativist, it's not a bad name for what he does. I'd hear his name every now and then, simulating the Big Bang or some natural disaster, either real or hypothetical. He started to become known as an astrophysicist, although that was only a part of what he was doing. Numerical relativist was one label I saw bandied about, but none really captured his real work. Sometime later, years before his work on the movie Interstellar, astrophysicist Kip Thorne, most of us have heard of Kip Thorne, I think, along with another astrophysicist, John Preskill, made a bet against Stephen Hawking. They bet that a naked singularity could exist. You've probably heard of the concept, at least. Very simply, if it exists, it's a black hole that has squeezed its own self out of existence, leaving only the gravity. Seems impossible, maybe, but they wanted to get some proof and win this bet against Stephen Hawking and win a T-shirt. So they contacted my friend Matt to provide the proof that they hoped would bring Stephen Hawking over to their side, which is a pretty tall order, but they moved ahead with it. In the end, Hawking gave all three of them T-shirts, but he also said that he was barely persuaded. In his words, he believed that the probability of a naked singularity existing was equivalent to the probability of a pencil balancing on its point, but he conceded enough to very graciously award the prizes. So my friend Matt did not make the bet, but he provided the proof. I never asked him what he did with his shirt, but he's a pretty smart guy. I would wear it once, be photographed in it, and frame it. Actually, I haven't seen Matt in a while. Next time I'm in Vancouver, I'll go and pick his brain, whatever, sure. Finally, scientific immortality. When you discover something, you get it named after yourself. And, if you don't have an uncommon name, it may not mean much. He has an unusual name. Top to it. It's not up there anywhere. Choptuik. I didn't even know that's a Ukrainian name. I've known Matt for 48 years, and I didn't even know that until about a month ago. Anyway, the Choptuik phenomenon. Approximately, it means that the formation of black holes has some similarities to a phase change in regular matter. That's a great oversimplification. That's my dumbed down grasp of it. Anyway, I don't envy Matt at all because I know he earned it. He's done very well, and I'm really glad to know him. Interesting guy. There is a link you can click on it to an article that tells you a bit more about the bet. In fact, if you read that article, it starts with talking about a different bet that Kip Thorne made along with Stephen Hawking. Later in the article is the bet that my friend was involved with. That's pretty simple, really. Any questions?
Is the article posted on the club's Facebook page?
I posted on the RASC Winnipeg page today. It's an article from the New York Times, February 16th, 1997, I think. The title of the article is "What a Physicist Finds Obscene," because that's what Hawking said about the concept of a naked singularity. And it also references the earlier bet, because the first bet, the prize was a one-year subscription to Penthouse magazine. Anyway, it's all there in the article. There's a couple of pictures of Matt, too. He's a great guy.
Oh, yes.
Okay.
Thanks very much. That was excellent, Matt. Sorry, Stephen. I called you back.
Stevenson.
Stevenson. It's
Yeah.
Matt Stevenson. Okay, Matt was your first name, though. Yes. Okay, thanks, Matt, again. Next up for Show and Tell 2 are two of our own regular members, long-term members, actually, Mike and Stan. They're going to show us one of the center's telescopes that we can all borrow if we've been a member for a while. So anyway, take it away, Mike and Stan.
How would you share this, Mike? I think Mike? Okay. Okay.
Mike gets the mic.
Okay, folks. Yeah.
we've started doing showcasing the loaner scopes last time, and yes, the lovely Stan is displaying it right now. Apologize for the folks at home. I'm going to be moving around a little bit, so you're not going to see my face. Oh, that's okay. So this time I'm going to showcase this nice little compact unit, and it's one that really hasn't seen a lot of interest in terms of powering it, which is kind of a shame because as you can see, the first thing about it, it's extremely compact. And Stan will give it a little lift. You see how light it is as well. Just a little. So it's really quite light. And basically everything for this scope can just be carried with this for the OTA and just a bag for the mount and the tripod. So what I think this is really handy, for example, for people that want to go very light, that want to perhaps take it camping, because usually trunk spaces are going to get a premium when you go camping. Everybody can find room for this little telescope, so it's really quite nice. And so what we'd like to do now is basically, I'm going to pop this. I forget to describe this itself here. So this itself is a 4-inch Maxitoff cast grain. And so what we have here is this is a fret meniscus lens with an aluminized spot in the center, reflective spot. And then so basically light comes in here, hits off the primary, off to the reflective spot, and then back through the eyepiece. The neat thing about this is that the reflective spot is also essentially your diagonal or your secondary.
Secondary.
Exactly. So it's permanently set, requires no collimation at all. And I had this out just a couple of days ago to try it out on a go-to mount. And collimation is perfect. It's bang on. And I was observing the moon and some double stars, and there was like zero chromatic aberration, no coma. The moon was perfectly silhouetted, and it was lit without any kind of signs of any kind of sign of chromatic. So it was really quite nice. And the sky background was really quite lovely too. It was nice jet black. So that essentially is this guy here. And what I find the best uses of this particular scope, and you can chime in here, Stan, too, but it's really made for more solar system objects, the moon, sun, double stars are wonderful with it as well. Because its full field of view is a bit narrower because it's a fairly long focal length. It's f12, and I think it's about 1250 for a millimeter. So it's got a bit of magnification with it as well.
Perfect for planetary.
Perfect.
You know, people, a lot of people always come around and say they want to get a scope to see the planet. And a lot of these new scopes that we have, these scopes, they want to see a planet, but they're very small. This scope has the longer focal length, so it'll work well, and it allows you to be eyepieces that have larger lenses. So when you're looking through it, it's easier to get your eye in there and be able to see the object as well.
Perfect. And because it has higher magnification, it's got a really unique little mount with it too, because this is actually a Vixen Porta 2 mount, and it's an alt-az mount. But the great thing about it, it has slow motion controls on it, and because when you're observing and you're splitting double stars and you're up 200 times, and I was actually over 200 times when I was doing the double stars, you can just adjust it very nicely with your slow motion controls, and it'll keep the object in the field of view, and that's a really nice little feature that this mount has. The tripod is a very rigid photo tripod, and I've seen a lot of photo tripods in my day. So this is a brand called Silk, and it's extremely rigid. And the reason why we mated it with this tripod, just because it really excelled at portability. You can just, like I said, you just pick it up with one hand, you put it away in just a bag. You're often off the races really, really fast.
Yeah. So when you're going camping and the wife says you're not taking that 10-inch Dobsonian into the car.
Yeah.
This is a scope to take for the summertime. So, and it is in the loaner program, right? So now's the time to plan on the scope. If you don't have a scope and you want to take something that's small and maybe take it with you, this is the kind of scope to take. And this is very nice. This is very, very easy to, you crank it over a little bit. And the other thing we're just going to point out is that in Scott's presentation, he was showing the finder scopes, and this is one of those zero power finder scopes. So you turn that on, it has a red dot. You align this with this scope, and it makes it quite a bit easier to find the objects. Go down here, you'll see the red dot, and you can
Get exercise as well. Might be smart.
Yeah. Does it take 2-inch eyepieces or?
No, just inch and a quarter.
Just inch.
Yeah.
And it has a small back to it. We have 3 eyepieces with it. It includes a 9mm as well. This is the 32. This is one of the super colossals. It's a very, very nice eyepiece.
Mhm.
And like you're saying, you're probably using the 9mm when you're looking.
Actually, when we were splitting double stars, I had a 5.5mm in it. And so I was over 200 times, which if you do the math, it works out to over 50 times an inch. Pretty good for a scope that's considered to be more of an entry level scope. What it also has is a cute little thing. I'll just show you a little more bling with this. You pull this out and it's got some Allen wrenches that are stored right here. So you don't even have to worry about taking extra tools if you need to adjust them out. Very handy. Kind of a red green sort of a touch.
You can lift it with one hand.
I'm using 2 hands because it's kitty, right?
I heard he's pretty strong.
It does work out.
Yeah.
Okay.
And then this also.
That finder is a little more convenient.
The finder,
What's that?
it's actually meant to encourage exercise.
Yeah.
But I think something on the list we'll have to do is actually pick up a little, perhaps a Rigel and just stick it on this part. So it's just gonna be a little more easy to handle. No, the one little downside about this kind of telescope, you notice, Chris,
Not so bad.
oh, the meniscus lens is fairly close to the edge of the scope. So in other words, you're gonna be getting some dew on it. And not to mention, even your light fluid environment, you're gonna have some reflections coming in. So just in addition of that lovely little flexible dew shield, which packs away really nicely. And then you're going to be shielded from dew as well as straight light. So this is a must-have. This is very important piece of specs we have. And I'm not sure what else to say about this thing.
That's what it is. Just a very simple scope to use. You want it first? Yes.
What's the procedure for members to book that, to reserve it? You just go over that?
Yeah, just actually on the website, you just have, there's a loaner scope tab. So just when you press that, it shoots me an email. So we just have to inquire, do that anytime you like. And if in case anybody does want to borrow it tonight, I do have a scope form right here. So don't be shy, come over and we can let you borrow it. Oh, good. It's loaned out apparently. That's awesome. Thank you. Yeah, it's on the website. In terms of what we have in terms of scopes.
Not in the groups.
It should, no, it's on the website. Okay, there's no more other questions. We'll wrap this up. Thank you.
Okay.
Just gonna mention one
go
thing,
ahead.
stuff like this and things on scopes, we've got a person within our club who's extremely active on putting things onto our Facebook page. No, it wasn't really mentioned today, but we've got a Facebook page. I took a look. We have 895 people on it right now. So there's a lot of people who are checking out and it's the Winnipeg Center Facebook page, and Wing is putting something on a daily basis, whether it be about scopes. He pointed out there's one that's up for sale, a 10-inch one telescope that's somebody's selling. So he's just providing information on that. So you may want to also keep in touch with us via the Facebook page.
Yep.
It's very active.
Excellent. Thanks, guys. I appreciate your time. We'll look forward to the next piece of equipment in our loaner program in the library. We're up to the break in our member meeting. So we'll take about, what time we got? 8:14, and our main presenter is on about 8:30, I think. Okay, so then maybe everybody back in their chairs by 8:30, that would be great. And we'll have our main presentation from Dr. Philip Ferguson speaking about making aerospace technology accessible. Thanks.
Is. Did we do that? Yeah.
Well, I used to. I know that's. But it's,
Worked pretty well. Does it give you a signal when the batteries are running down?
Yeah, I can see it there too.
Oh, I
It has the same display here, but I can see it too, so I.
thought it was okay while I was on.
I don't wanna be in the middle of the presentation, especially main speaker, and it's just like, we cannot hear you.
Yeah.
And I don't get getting. I don't think that if you want something viral, so I don't break for any of that. They all want to take here. Nice tension. A little bit of that.
That kind of now probably.
Yeah, so
Where he was like.
No email.
Well, you know, this is the mark of success, right? You get a Wikipedia article.
Oh,
Yeah, that's the picture that was.
oh, do you want me to join the Zoom call?
Yeah,
Why don't I do that? And
Yeah.
then I can, then we could, yeah, then we can mute your computer. Yeah. Did you get the, I believe I did. Okay, I got it from June. Okay. So actually, I'm just gonna make my other machine. Oh, good, my other machine is fast.
Wow, I think you probably got, yeah, up to 120. I have some checks for you. I didn't play it. Anytime.
And just really
There, that's better. You got it. Okay, cool.
Okay, we're on here, okay?
Okay, I'll take this
Okay.
for my students. You guys, come on up here. Come on up here. Why are the
All right.
students so afraid?
Dr. Ferguson, everybody. Let's get a walk.
Thank you. Happy to be here. All right, everybody hear me okay? All right, I'll use my professor voice. So, happy to be here. Thanks so much for inviting us again. This is, I was saying, you know, people ask me, they say, Phil, what do you do for a living? And I say, well, I speak for a living. You know, I write proposals for a living. I guess some people call me a professor, but really what I do is like to talk. But my favorite time to speak is to this group because I feel like I'm talking to my people. These are my people here, people that understand us, right? Understand us. So we've given a few talks before here at this event from the Space Technology and Advanced Research Lab here at the University of Manitoba. We've spoken about other CubeSats that we've done. We've spoken about student experiences. But today I want to talk about something that's really near and dear to my heart, and that is making space technology, aerospace technology, accessible. And now, when I say this at first, people think, oh, do you mean like for people with wheelchairs to get into space? And I say, no, that's not quite what I mean. What I'm really getting at here is, you know, as some of you know, actually, is there a way to turn down the lights? Because I know we had turned them up. I don't have stuff to. Perfect.
You can do AV, actually.
I think that's good.
How dark do you need it?
Oh, that's good. I don't want people to go to sleep. So, you know, as many people know, before I became a professor here, I worked for a couple of decades in the space industry. And I worked on projects like the Space Shuttle, like the International Space Station. I worked on the RASC Constellation mission, of course, built right here in Winnipeg, Manitoba. You know, Canadians put stuff on the James Webb Space Telescope. There's, of course, the Hubble and Sentinel-2. The problem is that these are fantastic space objects, space assets, and yet they serve such a few number of people, right? And the people that actually need to get access to space and aerospace technology, like communities in Canada's Arctic who are experiencing climate change 4 times faster than the rest of the planet, these people don't have access to this. They cannot afford images from RADARSAT Constellation mission. They cannot afford to get data from AIS, which is the automated information system that tells them when the ships are going to be in their communities next time. And those ships cause a big problem. They're scaring away beluga whales. They're making it so that they can't harvest food for their communities. And I thought, you know, something needs to change because while it's great, we're doing lots of great aerospace technology development in industry and around academia, we need to find a way to make it more accessible. We need to get that into the hands of the people that can actually use it. And so, you know, when we think about this and we think, well, you know what, in today's day and age, we've never had better access to space. Last year, we launched just a Falcon 9 rocket alone, launched over 130 times. This year, we're planning, just about 100 times. We're planning on doing more than 130, 140 Falcon 9 launches alone. But now we have other players like Rocket Lab. There's a new rocket, I think it's called Iris, that's going to be launching for the first time, I think, next week. So never before have we had so much access to get into space, which is fantastic, right? We used to only have the space shuttle, which didn't launch very often. But what I find right now is what we're lacking is in creating technology that can allow us to get stuff into space. So just to give you an idea of how much more we're launching right now, this is a plot, and I zoomed in on this just because it was getting a little bit ridiculous, but even just from 2010, so only 15 years ago up until now, look at the amazing increase in launch rate. These are just objects that we're putting into space, and yet, unfortunately, even though we're able to put more stuff into space, the stuff that's going into space is not being made accessible to the people that need them. Some of you may know I do a lot of work in the Arctic. I go to the Arctic a couple of times a year. I work mostly with Chesterfield Inlet, Nunavut, and we're looking to help them cope with climate change using space data and drone data. And so we're going to talk a little bit about that today. And that's really what this Space Technology and Advanced Research Lab, or STAR Lab, does, is we're here to make space accessible. I like to say sort of kicking the space industry in the pants a little bit and saying, come on people, we can do this better. It doesn't have to be the case that we're going to do billion-dollar space programs. Let's put satellites in space that only cost $50,000, $100,000. And let's put that satellite technology into the hands of communities and small research groups, small companies, small startups, so that everyday Canadians can get access to space. So that's what we're going to talk about. So I'm going to start with ArcticSat. So ArcticSat, this is an idea. Many of you probably knew Dave Barber before he passed away. Dave Barber was a prominent Arctic scientist here at the University of Manitoba, passed away in 2022. Dave and I had a dream together. We thought, you know what, we are going to work together and we're going to create a satellite just for Arctic remote sensing. And we're going to do it with communities. We're going to co-develop it with the community of Chesterfield Inlet, Nunavut. And that's exactly what we're doing now. We hire Arctic scientists to work with us. And when I say Arctic scientists, I don't mean people like Dave Barber. I don't mean people like Dustin Islifson that work in the Center for Earth Observation Science. What I mean are community members, people that live in the Arctic. These are scientists. These are engineers. You know, these are technicians. These people don't necessarily have PhDs. They don't have master's degrees. They don't have bachelor's degrees. Some of them don't even have high school degrees. And yet these people are researchers nonetheless. These people know the land. They know the water. They know the air. They know the animals. They know how the weather changes. And they know how their community is changing. These are researchers, and we treat them like researchers because that's what they are as members of our team. Much like the graduate students that I have here today, they are paid in the same way. They're paid stipends. They're paid research salaries to work with us on our team so that we can research these things together. Sometimes people ask me, they say, wow, come on, Phil, these are people that live up in the Arctic. I mean, what do they know about satellites? And I say, hey, I have never met more technically minded people, more scientifically minded people than the Inuit that I work with up north. These people know their land. If I ever had a broken down skidoo, I'll tell you, the first person I'm going to take it to is an Inuit person because they know how to fix things. They definitely know how to fix things. So what we're trying to do with ArcticSat is we will be developing the world's first community-operated CubeSat that will measure sea ice using passive microwave radiometry. Now, some of you are really into remote sensing, and you'll say, hey, Phil, that's old news. We do that all the time, right? Like RadarSat Constellation mission does that with active radar. Sentinel-2 does that with active radar. We can get so much better pictures from bigger spacecraft. And I say, yeah, and how much did that spacecraft cost? $1 billion. How many times do people actually operate that spacecraft from the Arctic? 0. None of them operate that. And how much data are they actually getting into those communities? Almost nothing. So this spacecraft, I was actually going to bring it with us today, but I took the students out for dinner before I came here today too. And I didn't want to bring it to the restaurant. But the satellite's about this big, right? And our dish is about this big. Right? Compared to the giant satellite dishes that are going in space right now, our resolution is going to be very small. And the challenge here is, will we get enough signal to noise ratio to make this useful? I think the answer is yes. We need to be creative about how we put this data together, how we stitch it together with other space assets, how we stitch it together with consecutive passes over Hudson Bay. But I think we're going to be successful because we have an entire community behind us, and we have the entire Canadian Space Agency and other teams across Canada that are working together. I mentioned this is a community co-development project. We often are going up to Chesterfield Inlet. We fly drones. We fly prototypes of our sensors over the sea ice over Hudson Bay. We train the youth on how to use these sensors, and they love it, right? I mean, we come, they teach us all about the Arctic. The hunters and trappers teach us about the kinds of ice that they see. This is safe ice. This is not safe ice. This inlet used to be open. Now it's closed. This inlet used to be closed. Now it's open. This is where the polar bears come. This is where the seals go. We learn together, and we come up with systems that we can do together because we're making aerospace technology accessible. That's what we're trying to do. This is an image that I took from Chesterfield Inlet the first time I took a trip up there with the youth playing in front of what's now become quite a famous little hut right by the water there. In fact, if you look really closely, you can see this actually says, "Welcome to Chesterfield Inlet, Northwest Territories." back in the days before before we created Nunavut. But one of the things that's changing very rapidly in Nunavut is shipping. You can see the ship in the background there. I remember I was standing out there once with the community members from Chesterfield Inlet, some of the town council, and they said to me through a translator in Inuktitut, they said, if I could know anything, it would be, when is the next ship? And she pointed out to that ship, and she said, when is the next ship going to be in my bay? And I asked her why she needed to know that. And she said, because the ships have scared away all the beluga whales. The sounds of the ships have scared them away. And they used to be able to harvest beluga whales in their bay. Now they need to go a 10-hour boat ride north to Nauyat in order to find the belugas. And they said, sometimes these ships drop anchor and they send little ships to shore, and they don't know where these ships are from. They don't know what they're doing. They don't know how long they're going to be there. And worst of all, they don't know how they would ever respond to an environmental emergency if they started spilling oil or diesel fuel. And it killed me because I thought, geez, you know, the Canadian Space Agency are world leaders in tracking ships from space. This is the AIS antennas I was talking about a minute ago, Automated Information System. This is the system of all ships. They send out these signals to each other so that they don't collide in the open ocean. But we can sniff those out from space and get a global picture of every single ship in the world, where it's going, what country it's from, what its bearing is, and how long it's going to be in some places. In fact, they use it to find pirates, because guess what pirates do? The first thing they do when they want to become all piratey, they turn off their AIS transmitter. So you see a ship that all of a sudden disappears in the middle of the ocean. Yeah, that raises alarm bells. So this is what we're trying to do. We're trying to improve that access. So what kinds of data are we expecting to get? Well, maybe something that looks like this. This is data from Sentinel-2. Our data is not going to be this high resolution, but you can see on the left, that's Chesterfield Inlet, the town of Chesterfield Inlet. And what we see here on the far right is deformed marginal sea ice. There's smooth landfast sea ice, and then we have the smooth river ice. And so what we're doing now is working with the hunters and trappers, the elders, the knowledge keepers. They're taking us out on the ice and showing us the kinds of ice that they see that we're now trying to see with our space systems. In the lower right there, there's a picture of a bunch of us in Chesterfield Inlet last April. We were there working with the youth, trying to understand some of the ice patterns, and then trying to find ways for us to detect that from space. I'm now going to introduce to you one of my master's students, Daniel Asante. One of the ways in which we improve accessibility of space technology is to find ways to allow lots of different people with varying backgrounds to work on space assets. So Daniel, come here and take it away. We'll get you all. Yeah. Probably the easiest thing to do, Daniel, is to just kind of hold this like a microphone. Okay, go for it. And then just click on the, just tap on the thing there, advance.
Okay, hi everyone. I'm Daniel again, and I'm a graduate student on Star Lab. Just an overview of ArcticSat. ArcticSat is a 3U CubeSat, and each unit has a dimension of 10 by 10 by 10 centimeters. And in this presentation, I'm going to be talking about the structural modular design of how we usually build our CubeSats. And looking at the design on top, since it's a 3U, we have each of the units stacked on top, making a 3U. And on the top right corner, we have the shell designs which we use for our satellites. The main idea behind this design is to ensure modularity. So in the sense that during assembly, integration, and testing, which is usually when after building the satellite and verifying all the requirements, we actually start to assemble everything together and test. The idea of this design is to ensure that each subsystem can be worked concurrently to boost the process. So in the sense that the person working on the power subsystem doesn't have to wait for, let's say, the ATCS or the payload person to finish maybe debugging what he or she is doing. So in the middle render, in the photo above, we have, for instance, the power module with the communication module. So in the sense that this unit acts as a standalone device, so you could usually connect like an external power source to it, and you could just do oil debugging and testing with it. And at the same time, the person working on the payload could take his or her own unit on the side to work with. If you look at the ArcticSat photo, the last green checkbox is usually it's currently where the payload is. So for instance, that also has a unit like this. So hence the payload person can just have his own unit on the side and be tested instead of probably waiting for the CDH lead or the ATCS lead to maybe debug something, but he can have his own unit to work on, and it basically makes things faster. And on the end, I have a transparent view of what's usually inside the unit. So you can see a PCB on the bottom, which is the power board, and it's used to power the whole CubeSat. Then we have the batteries and the transceiver used to help with communication, as well as the antenna. Lastly, another important thing to understand about this modularity is that it's meant for any type of mission. So depending on if you're into remote sensing, earth observation, and many more. For instance, for ArcticSat, its payload is a cylindrical passive radiometer. So if you look at the top right corner, that's ArcticSat's payload, and essentially this modular design, you can redesign it into anything you want. So if you need to have a camera or a payload, you just have to alter the geometry of it and it fits. So yeah, that's the main idea behind it. And on the side, we have Iris, which is Starlab's first satellite, which was launched into space. And its payload was supposed to help scientists study how space affects the composition of asteroids in space. So this same modular shell design was just altered to, sorry, just like I'm making so much noise with.
Just a little further away from your mouth, yeah.
Can you hear me like this?
Yeah, that's great.
Oh, you can hear me like this?
Oh, yeah, it sounds great. Yeah.
Sound like breathing it.
That's good.
Okay, so this is fine, right?
Yeah.
Oh,
loud and
perfect.
clear.
Okay.
Yeah.
Much better. I wish I knew this in the beginning.
Trying to find a way to tell you. But
Sorry. Okay, so once again, so Iris, its payload was to help scientists to study the composition of asteroids in space. So this same modular design that I showed in the previous slide was basically just altered to accommodate that sort of payload. So essentially what I'm trying to say here is that the structural design we made for our satellites is just reusable, and basically it's mission agnostic. So it can be used for any payload, any mission, and can just be swapped based on your needs. Yeah. Thank you.
Okay, thanks, Daniel. Excellent. So many of you are probably thinking, and if any of you were listening to CJOB shortly before we came here tonight, I was just on the radio speaking about a pretty prominent piece of space junk that's about to land in the middle of the night tonight from a Soviet-era Venus lander that never quite made it to Venus. However, be that as it may, I mean, we are legitimately launching a lot of stuff into space now. You know, Elon Musk on his own is launching several thousand spacecraft, has recently, and plans to launch another several tens of thousands of more. And these CubeSats pose a certain risk as well. Now, many people ask me, they say, oh, space must be getting pretty crowded up there. And it is, but I do want to remind everybody, space is pretty big. It's not like you're up there and you're looking at, you know, like an old wind-blown corner somewhere on Portage and Maine that's all stuffed up with garbage from the high winds. But there is a lot of stuff up there, and collisions in space are a much bigger deal than a fender bender, and somewhere in the middle of Winnipeg. These relative velocities are moving at several tens of Mach numbers, up to 30, 40, 50 Mach. And that means even a small fleck of paint crashing into another spacecraft can create a cloud of debris. And the challenge that we're facing right now is that at some point we will end up with so much space debris that these collisions will keep happening, and then the little pieces of spacecraft will collide with other spacecraft, and then those pieces will collide with other pieces. This is something known as Kessler syndrome. And Kessler back in the early 80s predicted that eventually we're going to have so much stuff in space that entire orbits will become useless. And so what we need to do is find ways to prevent this from happening. Now, the first thing that we can do to prevent this from happening is to work with countries to stop demonstrating anti-satellite technology. So this has happened before with Chinese weapons tests. It's happened recently with some Russian tests. It also sometimes happens accidentally, like when the Iridium and Cosmos spacecraft accidentally collided with one another. But the thing that really creates these huge step functions in space debris are the purposeful demonstrations of blowing up satellites in space, which is not helpful at all. Now, one of the satellites that we're building right now in parallel to ArcticSat is something called LISA. LISA stands for Little Innovator in Space Situational Awareness. And situational awareness really just means what it sounds like. It's trying to understand what's around us in space. And for many decades, our only way of knowing what's in space is by using ground-based telescopes and ground-based radar to track these objects. We're very limited in what we can track from the ground. We can only see objects up to about, or greater than about 10 centimeters across. Anything lower than that, we have a hard time seeing from the ground. And that's unfortunate because those small objects can make big problems, especially if they happen to hit exactly the wrong spot in the International Space Station. So LISA is a CubeSat that we're developing here at the University of Manitoba in Starlab. This is a joint project between the Defense Department of Canada and also the Defense Department and Research and Innovation Department of the United Kingdom. We're working together to demonstrate how small satellites like LISA can work together with larger satellites like the Red Wing satellite that Magellan Aerospace is building, how they can work together in tandem, flying in formation, taking pictures of each other, trying to calibrate their sensors, and then we'll be using these sensors to take pictures of spacecraft over Antarctica. Now you might say, well, why Antarctica? Why do we care what's happening over Antarctica? Well, the reason why we care so much is because that's one of the places that we can't see. We don't have a whole lot of telescopes over the South Pole, but we can put telescopes in space, and small telescopes, like small infrared imagers, like we're doing here on LISA. The image that you can see there on the right is from the Cassiope spacecraft, also designed and built here in Manitoba at Magellan Aerospace. They have an EPOP instrument that is operated by the University of Calgary, and they can see space objects as well. We're hoping to be doing this at a completely different level, in polar orbit over Antarctica. Now you may ask yourself, if we are working so hard to mitigate space debris, what are the governments doing about it? Well, so Canada plays a really strong role in this. So way back in the mid-90s or so, the United Nations created a new office. They called it UNCOPUS, which is the Committee on the Peaceful Use of Outer Space. And the very first ever chair of that committee was David Kendall, Dr. David Kendall from Canada, who used to be with the Canadian Space Agency. And one of the things that they came up with was very prominent. They made an international recommendation that all spacecraft shall remove themselves from orbit within 25 years of ending their mission. And at the time, that was pretty bold, right? This was coming out in the 90s. There weren't a whole lot of spacecraft in space at that point. And all of a sudden, there was this international rule that said, okay, we all have to work together. Now, like any kind of global rule, like trying to fix holes in the ozone layer or like trying to adjust climate change, we need international buy-in. And while many of the countries in the world do buy in right away, it's the countries that don't buy in that are a bit of a challenge. Now later on, this was in about 2022, the FCC in the United States came up with a new rule. They said, no, it's not, 25 years isn't enough. We have big problems in space. We have a lot of junk. We need to get this stuff out of space. We're going to call this, the United States put in a rule that said, no, it has to be 5 years. Now, since then, there have been some legal challenges about this, and many people wondering, the FCC is the Federal Communications Commission. Why are the people that are regulating radio being the ones telling people what they can and cannot put into space? However, so there are some challenges there, but I will say that Canada very recently, so earlier this year, are starting to propose very similar rules. And in fact, if you talk to David Kendall, and I had a great conversation with him earlier in the year, David told me that even the United Nations today generally feels that 25 years is way too long. Even 5 years is too long. With the amount of stuff that we have in space, we need better technical solutions to get stuff out of space. So one of the research projects that we've done, and this speaks to accessibility, because if we have space that we can't access because there's too much junk in there, then what good is space? So one of the ways in which we're trying to make space more accessible is by providing ways for people to remove objects from space. And this is an interesting challenge because we're building these tiny CubeSats. So we're doing these on a shoestring budget for a satellite that is about as big as a shoebox. And it's very difficult for us to make thrusters. And so we created a small 3D printed thruster using some technology right here in Winnipeg built by Precision ADM. Some of you have heard of this. It's a 3D printing company. It used to be called a startup, but they're not. They have started. They're doing very, very well. And so we worked with them to do 3D printed thruster modules that you can tack onto the end of some of these larger CubeSats, like LISA that we're working on right now. But many spacecraft even don't have space for a large thruster module like what I'm showing in the picture there. And so we've needed to come up with new ways to make other thrusters out of cold gas. So those little tiny CO2 cylinders that you would stick on the bottom of a fun little, airsoft rifle or a little paint gun or something. We have one of our students here, Elham Beneshi, who is working on cold gas thruster systems that we will use on the LISA spacecraft. So Elham, take it away. Just touch here to advance. Okay.
My name is Elham. I'm a graduate student at Starlab and working as a thruster design for LISA. Most of the propulsion system needs a fuel storage to storage the propellant, and most of them maintain pressure at high pressure. So to ensure the reliable integration with multiple payloads into a shared launch environment, launch service providers such as SpaceX introduce strict safety requirements. For instance, SpaceX verified that a system with pressure higher than 100 psi is considered as a pressure vessel, and such a system must have United States Department of Transportation approval, or otherwise it should comply with AIAI standards in design and manufacture procedures. On the other hand, the United States DOT Department of Transportation classifies a pressure vessels as a system with pressure higher than 200 kilopascals, around 29 psi, and such a system must comply with ASME boiler code. Regardless of this difference between these two thresholds, meeting this requirement for a system imposes high design factor. For instance, in the case of the propellant tank, it means increases the wall thickness and mass of the fuel storage, which is out of the scope of even a 6U CubeSat. So for LISA, in order to fulfill this requirement, along with staying with the mass and volume budget, we use a small bunch of CO2 cartridges and stack a bunch of them together and make the propellant tank. This design ensures that the complete compliance with both SpaceX and DOT pressure vessels regulation without any need for pressure vessel certification. The system is simple because it's use of off-the-shelf components, and also it's safe for university research base because it uses carbon dioxide as a propellant. Also, it's compact, as you can see, it's just conforming to one unit in a 6U CubeSat. But this safety and simplicity in design can provide a small delta V, and this is sufficient for collision avoidance maneuver. But if the collision avoidance maneuver would be the last minute action, maybe or probably this much of delta V is not suitable for that.
Okay, thank you, Anna. All right, so one of the other things that when I think about accessibility, I think about accessibility to technology. And I think about all of the thousands and millions of journal articles that we all write in academia. We stand up in front of people at conferences and talk about new whiz-bang algorithms and new fancy devices that we're going to put in space. And yet today, almost none of those things are finding their way into space. So on the one hand, we have this fantastic university research, and on the other hand, we have this industrial commercialization. And in this giant gap, we have real life things like risk and cost and schedule and hardware complexity, societal readiness. But more importantly, most importantly, the gap is confidence. So I work very closely with Magellan Aerospace. They're my primary research sponsor. They sponsor my research chair. And whenever I go to Magellan and I say, hey, Magellan, I got this great new thing. Well, how am I going to put it in space? And they say, well, how do you know it's going to work? And I say, I'm pretty sure it'll work 95% of the time. And they say, well, what about that 5% of the time that it doesn't work? And I'm like, it's okay, it's okay. How often is that going to happen? Like 1 in 20 times, right? And they're like, well, you know, that's pretty high. Right? And so they need confidence in these systems if they are going to put their name and their multi-million-dollar spacecraft behind it, even though we're trying to reduce those prices. And so a lot of the research that we're doing is how do we improve confidence? How do we improve the confidence in these technologies so that we can justify using these lower price systems in real commercial spacecraft? And so one of these things is confidence in navigation. I'm the father of a couple of teenagers. I'm sure that many of you have had teenagers. If you don't right now, you have in the past. And one of the things that I love is to find out where my kids are at any time, right? They can say, well, no, Dad, no, I'm at school. And I'm like, really? Because the phone says that you're at the mall, right? But what's interesting is that when I look at these pictures, this instills quite a bit of confidence in me. I can say, okay, that's good. So my kid could be on Grand Ave there. I don't know what city this is from. But they might be at the bus stop, they might be at that little place called the Patina, they might be on the other side of the street, they could be on West 2nd Street, I'm not really sure, but I know that they're somewhere in that circle. And so we have a very similar thing that we do in spacecraft navigation. We call this covariance confidence. And so every time we do some sort of an estimator or a navigation filter, these filters give us some kind of confidence as to how accurately we think that solution is. The challenge, though, is that in space, most of this estimation that we do is nonlinear. And so these confidences are not really trustworthy. So now I'm talking about sort of meta confidence, right? The filter says, I think that you're here, plus or minus 500 kilometers, but I'm only 20% certain of that. Right? And so somebody like Magellan looks at that and says, oh, geez, I don't know. I love your whiz-bang algorithm. It looks like it works good most of the time, but if I can't trust how well it thinks it's working, I don't have any safety net. And so a lot of the research that we're doing now is to try to find ways to make these filters more self-aware. A filter that knows when it's not performing well so that it can tell the rest of the spacecraft, I'm not performing very well, step in and use some kind of a backup system so that I have time to get myself back online. One of the things that I think is really interesting is that we see this a lot in nature, right? I mean, when a baby deer is born, they're born with spots. Their only way of avoiding predators is to sit down in a bush and wait it out. At some point, that animal becomes more confident in itself, confident in its abilities to run, confident in its abilities to signal danger to their other deer that are in the area, and it knows that it's capable enough to stand up and run away. And so one of the things that we're doing in my lab right now is to try to use machine learning and artificial intelligence to teach systems how confident they should be in their system so that they can inform the rest of the system and hopefully lead to better commercial adoption. Another thing that happens in space, and this is something that I think is endemic, and I've worked on so many different space programs, from the robots on space station and the space shuttle to the RADARSAT Constellation mission and space telescopes. And every single time we make a new spacecraft, we make it bespoke, like a pair of bespoke shoes. We are making this spacecraft for one purpose and one purpose only, and that means that we hire structural engineers, we hire thermal engineers, electrical engineers. We hire metallurgists and make sure that we have exactly the right optimal material that we're using for this specific mission. It works for that mission and nothing else. And so what that means is that we make specific structures that only work for this one mission. And then we take that structure and we build this $1 million spacecraft, 10 million, 100 million, $1 billion spacecraft. We put it on a big table and we shake the crap out of it. And then we hope that it doesn't break. That is expensive because we're paying all these engineers all that time, and then we're taking this expensive piece of hardware, putting it on a giant piece of magnesium, and then shaking the crap out of it. And so one of the things that we're doing now is we're saying, okay, well, wait a minute, what can we do better? How can we do that better? Can we use 3D printing to build small models of our spacecraft early in the design cycle? Build a tiny little 3D printed model of our spacecraft using a cheap little 3D printer, throw that on a small vibration table, shake it, find out if it works well, and if it does, then we can scale that up to a much bigger size and learn something interesting about that. I have a master's student right now that's just about to graduate on that, and he's looking at turning this into a PhD project as well, using very similar scaling laws like what people have been using for decades in wind tunnels, like the Reynolds number, for instance, which allows us to scale an entire Boeing 787 spacecraft down to a teeny tiny little model that we can put in a wind tunnel. This is the same kind of technology that we're talking about. But we're also using it to go the other way. The thing that you see on the very far right is a blown up version, a 3D printed version of a tiny little MEMS device. This is like a tiny little chip that is a gravimeter that we want to use on the moon. So this is a gravimeter we're developing with Simon Fraser University and the Canadian Space Agency so that we can measure gravity waves on the moon and look for different kinds of lava tubes that could support astronauts in future missions. These gravimeters are very difficult to test because they're so tiny and it's so expensive to build them. So we're looking at printing large versions of them, testing them at a big version, and then shrinking them down small again. So this kind of scaling law can go in two directions. Now, the last thing that I want to talk about, this is not really space, but it is space because it leverages space communications. And this is addressing some of the inequities that we have in this country and around the world when it comes to broadband access. So all of us, we take for granted the kind of connectivity we have right now. I'm sure some of you are looking at the Jets games right now. Are they winning yet? Hopefully they are. But we're all constantly connected to the internet. That is not true in the Arctic. And in the Arctic, every week in the wintertime, people go out to hunt and to trap and to provide for their families. And every week, those people get lost. I once asked some search and rescue people that live in Chesterfield Inlet, I said, how many times a month do you go out to rescue people? He told me they go out about 3 to 5 times a week to rescue people, not per month, per week. And many times these people don't come back. Now, a lot of people say to me, hey, Phil, this problem's been solved. These people, don't they have Iridium satellite phones? Don't they have InReach devices? Yes, that's true. When they pull that little button on an InReach device, it contacts somebody in Texas. That person in Texas calls somebody in Ottawa. That person in Ottawa calls somebody in Iqaluit. That person in Iqaluit calls somebody in Chesterfield Inlet. That person in Chesterfield Inlet tells somebody else to get on a snowmobile and go out and look for them. Those are seconds and minutes that those people don't have because they're in minus 50-degree weather. They do not have the same level of access that we do. And so what we're looking to do right now is to provide that access using satellite internet. Today, we're doing this with Starlink. I think it goes without saying that we're not really interested in being too reliant on Elon Musk and the Americans these days, so we're looking to move this to Telesat Canada's Lightspeed constellation. But what we're looking to do is provide this service via an airship, a blimp, a Zeppelin, something like the Hindenburg, but hopefully works a little bit better. And what we'll hope to do is have an actual cloud. I like to call this a physical cloud, providing cloud services. These giant blimps, I'm talking like 20-meter long blimps, will follow the hunters and trappers out on the sea ice, out on the tundra, provide them with high-speed internet from the Starlink or Telesat constellations right down to the handsets of those hunters and trappers. So now not if, but when they get lost, when they need help, when they suffer an appendicitis attack, when they have a compound fracture, we can do telerobotic surgery using high-speed internet from satellites. They can contact their loved ones, their elders, their community leaders, their healers in their communities, and solve these problems quickly. They can look at weather patterns that are coming around them. They can look to see how the sea ice is changing around them. Most importantly, they can be safe as we are when we go to the Jets party later tonight to celebrate their win. So this is exactly the kind of equity that we're looking to do. Access is the name of the project, stands for Arctic Community Connectivity for Equity, Sustainability, and Service. And one of the, there's so many interesting things about this project. There are social aspects, there's medical aspects, of course there's a lot of engineering as well. And the engineering that we're doing, I'm going to introduce here Mana, another one of my graduate students who is looking to do topology optimization to figure out how are we going to control these giant blimps in the Arctic. So take it away, Mana. Just click in the middle here, just tap there.
Yeah, for sure. Hello everyone, my name is Mana Zanbakili. I am a master's student in electrical and computer engineering at University of Manitoba. I'm part of the Access project, and in my opinion, one of the most fascinating parts of the Access is the topology optimization of the airship. So what I mean by topology optimization is figuring out how to place and where to place the propellers and motors so that we can move, hover and stay stable this airship, especially in the Arctic conditions. So one of the things that I'm doing right now is I'm using a particle storm optimization algorithm to figure out how many propellers do we need, where to place them, and at what angle. So the final goal is having full controllability while reducing the energy use and minimizing the system complexity, and also keeping the whole system lightweight and cost-effective. So after optimizing the placement of the propellers and designing the whole blimp and the propellers, the other thing that we are thinking about doing is controlling the blimp. So to do this, we have like several different control strategies. What I'm right now trying to do is that I'm exploring between different control strategies. So we have some conventional methods such as PID and FOPID, which has been widely used in industries for long decades and are well tested. But on the other hand, we have some AI-driven methods such as reinforcement learning, which is newer to autonomous aerial vehicles, but have been revolutionary in many industrial fields such as robotics. So I'm trying to kind of combine different methods together to build a control system that is robust to windy Arctic condition and can work for us for long missions and deliver internet to different remote areas wherever we are and in any conditions, in any windy conditions. Thank you. That was all from me. Thanks a lot.
Thank you. Now, the last piece that I want to touch on right now when it comes to improving accessibility is capacity. So the way that we are going to make space and aerospace technology more accessible across Canada and around the world is to train that next generation, the next generation of engineers and scientists and sociologists and artists that are going to move us into this next generation ahead of us. And so I'd like to bring Anant to the microphone here to talk a little bit about some of the work that we are doing to extend our training to different levels of students, including undergraduate and high school, graduate and postgraduate. And she can talk to us a little bit about the work that she's doing. So come on up, take it away. Thank you. So just tap in the middle of the touchpad there.
Okay.
Okay.
Hello, everybody. My name is Anant Kosa. How's everybody doing? Awesome. Okay, so I'm going to talk to you about how StarLab helps with accessibility to students from all different experience levels. So I'm an undergraduate student, and I came to Phil early January this year. I just knocked on a door and said that I was interested in learning more about satellites and doing more research. And he didn't even ask if I had any experience. He was like, "Oh, you're interested? All right, great, you can start." And so I think that that's something that's really unique about StarLab is you're able to build capacity from the ground up. It doesn't matter what kind of experience level you have. If you're interested and if you're wanting to contribute, there's space for you and there's room for you to be a part of this. We have students from all different levels, even high school students. We have interns who work on different projects based on their interests. We have students working on stuff with computers and coding and rovers and things like that. Mostly what I've been working on is thermal simulations. And I came into this having very limited knowledge about satellite design, but during my time here with StarLab, I've gotten to learn how to use different software such as Siemens NX and learn how to conduct thermal simulations for real satellites where we test different situations in space, detumbling when systems are on, off, hot, cold. And so StarLab is really helpful in giving you access to experiences like this. Okay. So capacity building is, you start off at an individual level and learn how to expand your abilities, but after that it becomes an opportunity for real-world applications. We have partners with Magellan Aerospace where students can gain industry experience. So it's not just theoretical, it's about actively contributing to real projects. And StarLab really helps to create pathways, not just for local opportunities, but for global opportunities as well. later this month, I've gotten an opportunity to attend a program with the European Space Agency in Belgium, and this is all through my work here at Starlab, which wouldn't have been possible otherwise. And so it opens opportunities up such as that. And we also work with organizations like the Canadian Space Agency, and so it really helps to give way to students to work with international organizations and competitions and to contribute to actual satellite launches. So overall, Starlab is really wonderful in making space technology accessible to all sorts of students, no matter your experience. Helps you to build your capacity from the ground up and creates pathways to global and international opportunities. And yeah, that's all. Thank you.
Well, so thanks very much. That's what we had for you today. This is a small sliver of the work that we have going on right now. In 2024 alone, we had 68 students come through Starlab. Those are not the students that I taught, right? So those aren't my undergraduate students sitting in the lecture hall. These are students that are doing active research in the lab. I'm really thankful to the support that I get from the Price Faculty of Engineering and from the Canadian Space Agency, of course, Magellan Aerospace, and the University of Manitoba here. And I'd be happy to take any questions about some of the work that we're doing at Starlab. So thanks for having us again today. Thank you. Yes, go ahead.
What's the duration or the functional duration of each of these smaller satellites?
Yeah, it's a great question. So it depends heavily on the orbit. So IRIS that we launched in 2023 lasted only 10 months because it was in a space station orbit. That's only 400 kilometers. And the northern lights that we're all experiencing right now, because we're in solar max, also tend to swell the atmosphere a little bit. And so satellites aren't lasting a whole long time in low Earth orbit. Now, ArcticSat and LISA will be in orbits that are approximately 520 kilometers high. So it doesn't sound that much higher than 400. However, that little difference makes a huge difference in the atmosphere. So those satellites are expected to last anywhere between 5 and 8 years in orbit. Trying to meet that 5-year deorbit rule is a challenge. It just means that we kind of have to extend our lifetime of the spacecraft so that by the time the spacecraft's life is done, we can guarantee that we'll be out of orbit in 5 years. So that means we have to use a little bit higher reliability equipment that we can continue to operate for, say, 3 years before that 5-year countdown begins. But it really depends. Interestingly, if you were to ask me that question 10 years ago, I would say that the thing that would limit most spacecraft is radiation. It used to be the fact that commercial electronics only lasted about a couple of years in space before they would get fried by space radiation. But one of the things that we've seen in the last 5 to 10 years is that because electronics are getting so small, the quality has had to go up so high that these new electronics, like the electronics that you'd find in a vehicle, like in automotive grade electronics, are performing so well that they can last 10, 15, even 20 years in space. And so we're seeing a huge shift right now, and this is one of the reasons why CubeSats and these small, inexpensive spacecraft have taken such a prominent stage now in space. Yeah, go ahead.
Is there a mission control center somewhere on campus to track and monitor all the CubeSats?
Yes, sort of. Yeah, my office. Yeah. No, it's not my office, but I can see it from my office. I'm going to try too hard not to get on a little bit of a soapbox about this, but I will say some of you are probably amateur radio operators in this room. There tends to be the Venn diagram of astronomers and amateur radio operators has quite a bit of overlap, I think. We do have an amateur radio station on the roof of the engineering building. We can use that to speak with space objects, like the International Space Station has a ham radio antenna, and IRIS, our first spacecraft, spoke over amateur radio. In the last few years, the Amateur Radio Union, the International Amateur Radio Union, has clamped down on their issuing of licenses to use in space. And this is because much like property on Earth, the electromagnetic spectrum, there's only so much of it, and nobody's making any more of it. And so organizations like SpaceX and the cell phone companies and all the other spacecraft that are trying to operate in space are vying for a very small amount of electromagnetic spectrum. And so today, the only way to get access to electromagnetic spectrum in the amateur band is if you have a spacecraft that is directly dedicated to developing amateur radio technologies. So gone are the days where a scientist can say, hey, I've got this fantastic science spacecraft. I want to use amateur radio to talk to it. They say, no way. Talk to somebody else to get your spectrum, but we're going to reserve our spectrum for the amateur radio scientists and the engineers. So while we do have a ground station right now and that we did use for IRIS, the next two spacecraft that we're building right now, ArcticSat and LISA, we are using commercial S-band. And an S-band ground station is not something that a university can afford. These are hundreds of thousands of dollars of dishes that have to track the spacecraft. So we'll be using dishes that are associated with Seacor. They have a dish in Inuvik, Northwest Territories, and another one in Happy Valley Goose Bay. And if I have my way in the next 4 or 5 years, I've got a big proposal on the way right now that would see more ground stations built across Canada's Arctic to support small companies, small communities, and of course research institutions as well. So it's maybe a little bit more of an answer than you were looking for, but yes, we have one. It's a little bit outdated for us right now because it is in the amateur radio. It's still very useful for the amateur radio group and they're doing great stuff with it. But in terms of space communications, it's getting more and more difficult to use. Thanks. Yeah?
Curious about the blimps. At what altitudes you fly them at?
Yeah, great question. So that is, interestingly enough, one of the biggest open research questions because it depends on who you ask. If I were to ask Transport Canada, they would say keep it as low as possible. Keep it away from the bush planes, the aircraft that are coming in to deliver supplies to Chesterfield Inlet. If I were to ask the remote sensing scientists that are putting imagers on the blimp, radio stations, they would say, well, we want to be a little bit higher, but we don't want to be too high because we want to get good resolution of our images on the ground. If I ask the Inuit, they say it can't be high enough because the lower it is to the ground, the more it's going to scare the caribou, the more it's going to scare the beluga whales. And if I ask the people that are doing the cellular communications, they say, keep it close to the ground, but not too close because we want to have a nice wide swath. So this to me is a really fascinating optimization problem that we need to do to try to keep as many people happy as possible. But I'll tell you, the most important people there are the Inuit because they're the ones that are living off the caribou and the seals and the polar bears and the walruses. We're in talks right now. In fact, just before I came here, I got another email reminding me that I have to keep working on my Inuit research application because in order to do research in Nunavut, we have about 4 or 5 different organizations that we need to clear our research through with, one of which is the wildlife organization. And so that is the driving one right now, which means we're probably going to be limited to well, I say limited, but it means that the lowest we can go is probably 200 or 300 meters. Which is higher than I would like for an airship about 20 meters wide, to be honest with you. But this is part of engineering, right? And it's part of engineering with community like this. So really great question. And I wish I had an answer for you right now. We just don't know. It could be anywhere from 50 meters to 300 meters, but I think it's going to be more on the high end. Yeah. Yep, go ahead.
Is there enough helium around? I thought it was in short supply.
It is, and that's a great question, and it will not be helium. This will be a hydrogen blimp. Now, I say that, and many people have images of the Hindenburg, and they say, oh, yeah, I didn't think you were allowed to do that anymore. And I say, well, yeah. I mean, it's interesting, right? Because the Hindenburg disaster made a whole lot of people overreact and say, wow, obviously hydrogen was the problem. That wasn't really the problem. The problem was unpure hydrogen, right? If you have very, very pure hydrogen with no oxygen, there's no problem, right? The problem occurs when you have hydrogen mixed with oxygen. Now, there's no way that we could get enough helium. Like you say, helium's in short supply, and not only that, but it's also very expensive to ship that much helium up to the Arctic. So we will be using weather stations that are already filling hydrogen balloons for weather balloons. There is not a weather station in Chesterfield Inlet, but there is one in Rankin Inlet, which is just about 50 kilometers to the south of Chesterfield. So our plan right now, although I am working very closely with Mana and Daniel on this, is to fill the blimp in Rankin Inlet and actually fly it up to Chesterfield Inlet and moor it there in Chesterfield Inlet, and then work with hunters and trappers and move it out onto the tundra. But we'll be using hydrolyzers. We'll be generating hydrogen from the air in Rankin Inlet. So we won't be shipping any hydrogen there. But we're definitely not going to be drawing upon the valuable helium resource in this country. Great question. Thank you.
Another question.
Yes.
These equipment or devices, they choose power or energy from where, like, as the source of energy.
Yes.
Is it air? Is it batteries? Is it sun? Is it what?
So it's not the sun, because in the wintertime, there's not a lot of that sun. Everything that makes the astronomers very happy in the wintertime makes solar power generation very sad in the north. And so we will not be using solar power. We will be using batteries. Now, interestingly, we do have a battery expert here on campus. Dr. Christian Koos is a battery expert who looks into different kinds of battery chemistries like lithium ion, lithium polymer batteries. So we will be using lithium style batteries. One of the benefits of using airships is that it's pretty inexpensive for us to lift a whole lot of mass, right? So many of you have probably heard of, or maybe you know, Barry Prentice. Barry Prentice is a local Manitoba expert, and actually a Canadian expert in airships. And the kinds of weight that we're looking to lift with this airship is probably only 200 to 300 kilograms. Pales in comparison to the several tons that Barry would like to use to carry cargo up north. But most of the weight that we will be lifting will be in batteries. Now, you would be right to say, well, even 200 kilograms worth of batteries doesn't last a whole amount of time. But you'd be thinking mostly about drones. So when we fly drones today, those drones have to spend a tremendous amount of energy just staying in the air. A blimp stays in the air for free because we're getting that lift with the hydrogen, right? So we're able to be extremely energy efficient with the blimp. And so our thinking is that we can stay aloft and control ourselves for 1 to 2 weeks with a large pack of lithium-ion, high-efficiency lithium-ion batteries. Now, these batteries will get cold, and so some of the energy will need to keep those batteries warm. If you've ever tried to use a cell phone in the cold weather, any ice fishers know that your phone doesn't last too long when you're out on Lake Winnipeg, and so we'll need to keep these batteries warm. But this is all part of the systems engineering that we're working on right now to try to solve that problem. It's a great question. We do need energy. Yes?
Just at one point in your talk earlier on, you talked about a CubeSat looking at sea ice thickness.
Yes.
So I'm just wondering if you can talk a bit about that, sort of two parts of the question. One is it radar that's being used? And then secondly, you compared it to RadarSat, like how does the resolution compare, I guess, given that you have a smaller dish or whatever as far as aperture, radar aperture?
Right. So what we're talking about with ArcticSat is passive microwave radiometry. So we are not sending a signal to the surface and looking at a bounce. We're looking at the natural radiation from the ice that we're picking up from space. So right there on its own, we've got a whole lot less resolution. Unlike RadarSat that's putting 2+ kilowatts of energy down to the surface and bouncing that off and then measuring it again from space. RadarSat's resolution is, I don't know, somewhere on the neighborhood of a few tens of centimeters to several meters. Our resolution is going to be, it pales in comparison. We're like a pixel for us is going to be maybe 10 kilometers, right? So very, very large. We'll have a very large swath of data. One of the challenges that we'll be doing with this is to try to find ways to get better resolution out of that data. And we can do that in a number of ways. We can pair that data with other data sources, like RadarSat, for instance, if we can get that data source and then we stick these two together. Before Dave Barber passed away, he would always say, the challenge isn't so much spatial resolution as it is temporal resolution, right? So just getting more data more often, even if it's at a lower spatial resolution, is what's important, especially in the shoulder seasons when ice is being formed and when it's breaking up, because those are the dangerous seasons anyway, when people are trying to travel on the ice and they're looking for the dangerous portions of the ice so they don't fall through. So that's part of it. But then the other part too is in a signal processing perspective. So maybe I need 4 or 5 or 6 passes of data in order for me to stitch all these together and come up with a higher resolution image. One of the things that we're interested in doing is saying, okay, if it only costs us $80,000 or so to put one of these spacecraft up in space, what if we did like, say, 10 of them, right? We're still less than $1 million, and we've got 10 of them that are now flying in formation, and each one is taking a picture every 5 or 10 minutes. And we can stitch those together from a signal processing perspective and come up with a reasonable image that we can share with communities. And now they're doing this for less than $1 million, where they used to have to stand in line and wait to buy data that was taken from and over their own communities. There's a data sovereignty issue here, which is just tremendously terrible. But we're looking to try to put that data in the hands of these people that actually own it. And what we're hoping is that we can come up with algorithms that will allow us to stitch that together. So you're absolutely right. This is a huge challenge. It's a challenge from a signal to noise ratio perspective. It's a challenge from a resolution perspective. But it provides so many benefits from an accessibility perspective that we're looking to sort of stretch the state of the art in many different ways of like data analysis that will allow us to make use of this, frankly, I'll be perfectly honest with you, totally subpar data, right? And this is the thing, whenever I stand up in front of other people and I talk about this, oh, look what I'm doing. They're like, are you kidding me? That resolution is terrible compared to what we already have. And I say, yeah, but what we already have is not useful for communities. So let's find a way to crack that nut. So that's really where we're going with it. It's a signal processing issue. And I think it's, how do we be creative to make this work? That's what we're trying to research. Yeah, no problem. Yes?
One last one.
Sure.
We're talking about, I guess, imaging over the ice. Is there any imaging under the ice?
Yes, there are. And you know what? I mean, my wife tells me, Phil, you need to learn a really important word in the English language. It's no, right? and because I say yes to everything, I mean, you probably saw that. I'm just such a curious guy. But there are people that are doing research that I find totally fascinating, which is like underwater, autonomous underwater vehicles, AUVs. These are little submarines that fly under the ice, and they do some work there. Yeah, absolutely. There are people. We're not doing it here. Would I love to do it? You bet. And we've got a few proposals underway of us thinking about ways in which we can do that. One thing that I will say that we are doing, and it's not at all in this project, but we just started it yesterday, is I've been reached out. The Department of Fisheries and Oceans came to me and said, Phil, you seem to do a lot of stuff with drones. Can you find a way to design a drone that will shoot darts at whales to attach tracking tags to them? I'm like, how could I say no to that? Like build a drone that flies in the Arctic that shoots little darts at whales. But you know, it's an interesting problem, right? Because the way that they do it now is they bring a bunch of hunters and trappers in a little motorboat, and they are shooting the side of the whale. And that's not where they want those tags. These tags have GPS receivers. They have to look up, right? And that's not where the hunters and trappers are. And there is a company, it's called Snotbot, that was made in the United States, and they drop little suction cup things to the backs of beluga whales, which are really nice and smooth. But those suction cups only last for about 5 hours, and the scientists want more than that, right? So we're literally designing drones that will shoot darts at whales. What could possibly go wrong, right? But we're starting that right now. So yeah, great question. Yes, Judy.
I'm really interested in the confidence, navigation confidence.
Yes.
Because personally, I've run into a couple instances where navigating with Google Maps or something like it seems to be going great, and then all of a sudden you realize you are nowhere near what you were supposed to be.
Yes.
And there's no way to inform Google that there's a problem that'll do any good, and there's no way to find out that it isn't working.
That's right.
Until you are so lost that you backtrack completely.
That's right.
So, Google should be funding that work.
Sure. Wouldn't that be great? They got a lot of money. Yeah.
They did a traffic study. You did the little things that traffic was still there.
Well, not in the middle of Outback.
No, not in Australia.
Yeah, not in Australia.
So there are many things that we do day to day.
Yes.
Where we have to trust that it's gonna go okay.
Yes.
Like even communicating with 3 people, you know, you do this, you do this, you do this, and let me know when it's done, and then I get to do this, and then I get, you know, you'll tell me what you're doing, and how it will work out the next step.
Yeah.
Well, if one of them decides they don't have to reply, you're up the creek. So that whole confidence navigation of communication and of location
Yes.
is really important, and I can see what you're wanting.
Absolutely, it is, and you know, one of the things that I'll say too, and I'm gonna make fun of students for a minute now, so no disrespect here, but if you were to give students two different displays, a digital display and an analog display with a little needle, right, that points at a number on a graph, and you ask them which one's more accurate, they'll almost always point to the digital one. But who says that's the right one, right? It's just a bunch of numbers, right? And it's so hard to tell, and I mean, I'm not going to get into the politics of misinformation and fake news and everything right now, but it's related, right? How do we know what is true, and how do we know what to trust? Right. These are fascinating questions that, as technology grows and grows and grows, I feel like we're sort of, we as in the public are having the wool pulled over our eyes a little bit, saying, oh, trust me, no, this is the right answer. Look at how fancy the display looks. Look at how accurate these numbers look. Look at how often they're changing, right? And so it's so easy to fall into this false sense of security, saying, I know where I am. Like following some dirt road, and all of a sudden you're stuck up to your axles in mud because it took you down some farm road between two farm fields, right? It's happened I live out near Enola, and it happens to people out where I live all the time because they're following a GPS. And so I mean, as pain as it is for it to happen to us here on Earth, imagine how bad that is if you're up in space and you're trying to control a $300 million spacecraft. These are big problems, right? And it's these problems that are holding back the space industry right now. A colleague of mine, Rob Z, that some of you might know, he runs the Spaceflight Laboratory from the University of Toronto. He says that there's these two cycles that he talks about all the time, the vicious cycle and the virtuous cycle. The vicious cycle is that we are so afraid that space systems are going to fail. And so we build and we build and we build and we test and we test and we test, and we're so afraid it's going to fail, we put old technology into these things, right? Because we don't want to try the new stuff. What if it doesn't work? We only get one opportunity to do this every 10 years, and this opportunity costs us $1 billion every time. And because it costs us $1 billion and it takes us 12 years to do it, the government can only afford to do one every 12 years. And every time we get a new one, we're so terrified it's going to fail again, we just drive ourselves into the ground like this. Yet the virtuous cycle is we say, you know what, let's embrace failure. Let's build spacecraft a little less expensively, but it'll allow us to build more of them. And look, I'll be the first to say, did IRIS work perfectly in space when we launched it? No, it didn't work very well at all. But we learned a lot. It did work a little bit, and we learned, and now we've got 3 other spacecraft that we're building right now, and so we're learning. But the mistakes that we made on IRIS cost us $40,000, maybe? It didn't cost us $4 billion. And so we're allowed to build more, and we can graduate more students, we can train more students, we can learn more, we can afford to push the envelope a little bit, try new technologies, get it in space. And because we can do so many of them, we can keep pushing that needle higher and higher and higher. So the answer, I think, to your question is we need to question what we see. We need to be leveraging technology today like artificial intelligence that doesn't just try to tell us the truthiness answer like ChatGPT. Trust me, I know what I'm talking about, but actually train systems so that they know when they're failing, right? And that's something that we're starting to see now. In the last round of NSERC Discovery grants that we just submitted from engineering, I'd say probably 1/3 of them were about confidence systems. I'm up for renewal this year, and mine is all about confidence as well. I would say about 1/3. I was on a lot of the review sessions. A lot of people are thinking, how do we know when it's right? And I think this is refreshing, right? Yeah, I think it's really good. So we're moving in that direction. Are we there yet? No, not even close. Not even close. But I think the trajectory is positive. So that's where we're headed. All right. Thank you. I appreciate your time.
On behalf of Royal Astronautical Society, Winnipeg Center, thank you very much.
Thank you so much. I appreciate it. Thanks for having me again.
And thank you all.
All right. Thank you.
Thank you.